Right, Benjamin says no. All right, so I know that the conservative work is equal to the negative change in potential energy. I know that work is the integral of F dot d, we'll use R this time. The conservative force dot dr is equal to the net equals negative U final minus U initial. And what is the force? Besides gravitational force. I was thinking we did the formula for the generalized gravitational formula. You just can't find it in your notes. You said you think we did?
I think we did.
Okay.
If it involved like G M1, M2 over R squared.
That's the one. So I know that as this moves that way, my dr is in that direction. But my force is in the opposite direction, so my dot product here is going to produce a negative value. So this is negative integral big G, mass of the planet, mass of the object over R squared, dr. Equals negative UF plus UI. And just to warn you, I've done this derivation many times, and probably 80% of the time I screw up a negative sign somewhere, so be on the lookout for that. I pulled the constants out, so I got negative big G mass of the planet, X for planet, mass of the object, integral dr over R squared is equal to UI minus UF. And what's the integral of dr over R squared? Or if it helps, the integral of R to the negative 2 dr.
What makes it negative, the whole integral?
What makes this negative here?
Yeah.
I'm doing a dot product. And if I have a dot product, flashback, A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them. In this particular case, FC and dr are in opposite directions, so it's 180 degrees. So you get just the force, the magnitude of the force, times the magnitude of dr, times the cosine of 180 degrees, which is -1. That's where it comes from. As a general rule, if the force and displacement are in opposite directions, it's negative. So from some R initial to an R final. All right, so the integral of dr over R squared,
Negative R to the negative 1.
okay? So that is negative R to the negative 1 from Ri to Rf. That negative and that negative should cancel out. So I'm left with big G MXMO times 1 over R final minus 1 over R initial equals U initial minus U final. Distributing, I get GMXMO over R final minus GMXMO over R initial. And I have not screwed up a minus sign. So what is a formula for U that would satisfy this? question on the floor is, what formula can we use for U such that this is valid? I don't know if that makes it clear. Because the numerator is just some constant for a problem. Come on, take a stab at it. What's the worst that happens? You're wrong. The best that happens, you're right.
U final plus U initial divided by 2.
No, looking for just U such that when I look at the final stuff, I get this, and when I look at the initial stuff, I get that.
It wouldn't be MGH, would it?
No, not, no. Because MGH assumes that little g is constant, and little g is not constant when you're dealing with outer space like that. Unless, it would be a limit. If RF and RI were really close to each other, then we should be able to come out with an MGH. However, we are not making that assumption. All right, if I did U final minus U initial is equal to X final minus X initial. Let's make it 2X final minus 2X initial. What would be a formula for U such that this would be valid? You're going way complicated there. Parallel.
2x.
2x, yeah. If U is equal to 2x, this works. So over here, or if I did U final minus U initial is equal to 2 over X final minus 2 over X initial, what would be a value, what would be a formula for U that would make this valid?
2 over x.
Say it again?
2 over x.
Yeah. If I throw it around so that U final minus U initial is equal to negative A over X final plus A over X initial.
Negative A over x.
Yeah. And that's what we're working with right here. If I just multiply this, everything by -1, we get that. So, what we end up with is that a formula that will work is big G, mass of X, mass of the object, over R. This is, negative. The important negative. If I launch something from the planet, starts out with all this kinetic energy. Starts out with kinetic plus potential, but as it goes out, what happens to an object the farther away it gets from the Earth?
There's less pull, less gravitational force.
Okay, and if I throw an object up into the air, what happens to it as it goes up? Besides less gravitational pull.
Slows down.
Yeah, it slows down. So as this goes out, this has to get smaller. If I'm launching it from the planet, there's no rocket boosters or anything like that. It goes shooting out like that. So kinetic energy is dropping, therefore my potential energy has to increase. Well, R is getting bigger. As R gets bigger here, what happens to U?
It's smaller.
Why?
This is an inverse relationship. So it'll be divided by a larger and larger number.
That is true. So you're saying this is all bunk, that physics is wrong, or I made a mistake somewhere. Because as kinetic energy drops, potential energy should be increasing. Like you just said, you divide by a larger and larger number, U gets smaller, except why is U getting bigger?
Because it's negative.
Yes. Because as you go from -4 to -3 to -2, we're getting bigger numbers. So it does work in that respect of, we've got to have the negative sign. If the negative sign weren't there, would not work. Because they would both be getting smaller as you were going for. So we now have a formula for potential energy, and as always, plus some constant. Because the difference, that constant's going to cancel out. And it gives us the freedom to pick wherever we want 0 to be, and typically, doesn't have to be, but typically, you establish 0 to be an infinite distance away. Because again, what's really critical is the change in potential energy, not the actual value itself. Unless, of course, you're asked, what's the potential energy? All right, questions there before we actually use this. We are going to derive the Schwarzschild radius, in other words, the size of a black hole, using classical mechanics. And surprisingly, you get the exact same answer as if you were using general relativity. Questions? All right, I have a planet here. I'm going to launch an object. However it gets up to that speed is of no concern of mine. I just know that this thing is shot off at some initial speed, v sub I. And I want to know that how fast does this need to go in order for never to return? We are dismissing air resistance. We are also dismissing anything else in this universe. It's just this planet and this object. So right now we're just deriving escape speed. Well, let's look at the energy. I have kinetic initial plus initial potential. And then somewhere over here, I've got kinetic final plus potential final. So, what's the formula for kinetic energy?
1/2 mv squared.
And what's the formula for potential energy?
Which one?
The one associated with the generalized formula for gravitational pull.
MGH. Oh, wait.
That's
Excuse me.
the other one. Generalized equation.
Make a big G. MXMO over R. Plus a constant.
And I'm not gonna bother writing that part. Well, you know what, I'll go ahead and write it and we'll just get rid of it quickly. And that's gonna be equal to, well, the same formula is just final, so 1/2 mv final squared plus negative g mx mo over r final plus c. And c cancels out. All right. Can we get rid of anything? Or actually, what can we get rid of?
Mass.
Okay. I did not label it real properly. That's the mass of the object. That's the one that has the speed. But we have m sub o in every term. All right. Anything else? Let's go step by step. Is the initial speed 0? I hope not, because otherwise it's no problem. We have an object, it sits there. R sub I, is R sub I 0? What is R sub I? If I'm launching this thing from the surface of the planet, what would the initial radius be?
Is it to the center of the Earth, or to the center of each object, or to
Yes,
the,
center to center.
so it would be the length of the tiny thing's center, or its radius, and then the big one's radius.
Okay, we will assume that the tiny thing is so tiny in comparison to the big thing. So just radius of the planet. Final speed. Is it 0?
Shouldn't be.
Okay, why not?
There's nothing to slow it down.
Say it again.
There's nothing to slow it down.
Well, we still have the gravitational pull.
Okay.
We're hoping it's not gonna return, so if it hits 0, it might start going back the other way.
Yeah, if it does actually hit 0, it will start going back the other way. However, this is physics, not math. It's gonna be small. I don't know what it is, but I know that it's gonna keep slowing down and slowing down and slowing down. So this is 0 because v sub f is close enough to 0. But it will never actually equal 0, it just gets smaller and smaller. And on top of that, we're squaring it, which makes it even smaller. So that term right there, we will ignore. And this term, as Rf goes to infinity, because we never want it to return, so it better be, Rf better be getting bigger and bigger.
The whole term gets closer to 0.
So that approaches 0 as well as Rf goes to infinity. So what we're left with is a much simpler 1/2 v1 squared is equal to, actually let's keep, minus big G mass of the planet over the radius of the planet equals 0. So we very conveniently have a formula here for the escape speed. So this escape speed being how fast you need to shoot it directly away from the planet in order for it never to return. And that's going to end up being the square root of 2 big G mass of the planet over the radius of the planet. Make sure I didn't lose a square somewhere. All right. So for Earth, this is the square root of 2 times 6.67 times 10 to the negative 11th Newton meters squared. I'm going to run out of room. So V equals the square root of 2 times 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared times the mass of the Earth, 5.98 times 10 to the 24th kilograms, divided by the radius of the Earth, which is 6.38 times 10 to the 6th meters.
Meters per second.
I got that too.
I know it's a little bit more than 11,000, so that's feeling good. All right, so if we can shoot something more than 11,000 meters per second and it doesn't hit any air on the way, it will never return. And occasionally there are things that do reach that speed because you've got all sorts of molecules, gas molecules in the air, gets hit by radiation, it will speed up. If it doesn't hit anything else, it leaves. Fortunately, we can replenish that gas as well as we gain extra mass. All right, so that's the formula for escape speed. Now, suppose we took the Earth and compressed it down. Somehow magically we can take the entire mass, keep that mass, compress it down without it exploding. At what point will nothing ever escape? So, and this brings in sort of a semi-classical limit here, although there was some speculation before relativity came along. If the maximum speed that any object can have is the speed of light,